we did our best to make a demo of something that closely relates to what was discussed and what was explained with our guest lecturer Alvaro. So today in our demo, we are going to use two external controllers. You can see them here on the webcam. One is going to be Texas Instruments F2808 controller, which is going to drive the energy storage inverter. And another one, also from Texas Instruments, F28377, that we are going to use as PV inverter controller. So the small schematic is here for you to see. Everything that we do today, from modeling to compilation and finally running the system and testing different testing scenarios, we are going to complete in the same environment without using any third-party tools. So the similar schematic to the one that you saw in the presentation slide, you can also see here on the screen. So we are going to simulate a grid with a bit more detail, meaning we are adding some transmission line models and few switches that we are going to use to simulate different faults on the side of the grid. And as well, we are going to simulate one generator model so that we can easily switch from grid to the island mode and see and verify the behavior of our converter controllers when they are disconnected from the grid. So all of this that you can see right here is modeled in the same environment completely graphically. So as we are speaking about highly specific testing equipment, we had to make quite a straightforward and relatively easy way to model these kind of circuits without having to learn a new programming environment or without writing one line of code. Because we have to make sure that all the models that we are using in our tool, as this is a testing equipment, we have to make sure that every model is heavily verified, that every model performs quite close to the real-life applications, and then at the end it has to be easy for the end users to assemble the circuit that they would like to simulate. So in this case, we are going to simulate an energy storage converter here. If we go deeper in the schematic, we can take a look at the actual structure of the converter that we are going to simulate, also the filter. And here is the converter that is going to be controlled by this controller 2808 here outside. Every one of these models that you can see here in this circuit is a part of the modeling library that you can see on the left. So if we are speaking about converter models, you can see here that there is a list of common converter topologies already packaged as single blocks. Those are the ones that we are going to use today. So you can see that we have some single phase, but also three-phase converters, two-level, three-level, pretty much any common topology that we came across and that was demanded or asked by our users from the field. We modeled it and added to our library. Of course, there are also some simpler models like simple IGBT leg, or for example a boost, or a buck, or a thyristor leg that end users can combine to make more custom topologies to match their applications. For very specific topologies that are sometimes not covered that are not that common, or sometimes are protected with the IP. In this case, you have an onboard modeling team that works closely with the end users to make specific models available for their library only. So, aside from the converters, there are also pretty much any passives or different contactors, different circuit breakers that also can be controlled by the external controllers. So all of this is inside, including as well the machine models. So this is the part of modeling the power stage, something that we are going to run with extremely low time steps in order of 1 microsecond or sometimes even faster. This example that you can see right here, all of this we are going to simulate with 1 microsecond update rate. Again, to further customize these kind of models, there is also additional layer of modeling available. We call it signal processing. This is something probably very similar to Simulink for those of you who worked with Simulink. You can see different discrete functions or custom C blocks that then you can further use to even design your controllers in some early stage of development, or further model the loads for the machines or something else that you may need. For example, here we have also a power meter, power measurement element that is partially modeled in signal processing layer. The difference is signal processing is running on different co-processors inside our boxes, meaning there is more liberty in this layer, as you can also define the blocks by just programming in C if you find something missing, and you can also define your own time step for running these kind of simulations. So this is going to be the system that we are going to simulate today. We can click the compile button. It will take maybe 1 minute or a bit more, and all of this is going to be converted to a real-time model, and it's going to be downloaded on our box, on our Typhoon HIL 602 that we are using today. And these converters are being controlled by these external controllers. So while we wait for the compiler to finish, let me just show you how we are interfacing our controllers with the converters. So for our energy storage converter, we are going to use quite common 3-phase 2-level IGBT converter. If you want to take a look what is behind, we can open a schematic library document that explains all models we have in our library. I'll just go to the table of contents and find the model that we are going to use today. This is a 3-phase 2-level inverter. If you take a closer look what is behind the converter, you can see that this is quite a common topology, and behind this block we see that there are 6 switches. 2 for each phase, phase A top and bottom switch, phase B top and bottom switch, and phase C top and bottom switch. On double click of the converter, you can see that we get the list of all the switches that are inside the converter. Next to them, there is a number of the digital input you want to use to send the firing pulse or PWM signal from your controller to the HIL, to the simulation. And that's it. This is how you're handling, how you're interfacing your controllers to the simulation. Of course, every one of these models can be further customized. For example, we can model the delay of the switching hardware, so it can resemble more closely to some actual real-life hardware that we have in our lab. Also, you can model thermal models, etc. And this applies to every model we are using in this circuit. For example, if you double-click on the battery models, okay, our model is compiled. Before we start the simulation, I just want to show you one more thing. Every model that we have can be further customized just by changing the parameters of the technical specification of the model. If we take a look at the battery model as example, we can see that there are some predefined battery types commonly used already available, but also there is a user-defined option where you can change the parameters just by its technical spec, just by changing the specs of the battery. Also, you can design your own charge and discharge curves. So this way you have the liberty to customize the models to replicate or to behave more closer to something you have in your lab, without writing even one line of code. So you can see that the model is done. You saw that the compiler is completely automated, so there is no need for end users to work with any complex FPGA programming toolchains or anything else. These processes are completely automated. So this is going to be the model of our solar inverter. So we have a bit more complex topology that is going to be controlled by this this controller right here. This is a 3-level T-type inverter that is going to connect the solar panels to the grid. On the side of the load, we are going to simulate one constant power load. We can change the load power during the simulation, and also another load in the form of the induction machine that can, for example, be some industrial fan or anything else that you need for your application. So let's start the simulation. All you need to do before starting the simulation, once your model is assembled, is just make the initial settings for the sources and map the feedbacks for your controller that your controller is going to read from your HIL. For example, how we can do this? Well, let's undock this control mapping window and try to see where it connects to our simulation. For example, if you want to send these currents IA1, for example, as a feedback to your controller through the analog outputs of the HIL, you can just go to the analog output settings, choose the number of the analog output, for example, analog output 1, and just type IA1. This is in the block of the battery storage inverter, and set the scaling and offset for this signal. This current is going to come back as a feedback to your controller. And this is it. This is how you are closing the loop over your control. So we have digital inputs that are going to read the fire impulses from your controller with 20 nanosecond time resolution. So the update rate of our digital input is going to be 20 nanoseconds, so it will support also very high PWM switching frequencies. And then the feedback is going to come back to your controller in 1 microsecond update rate in this case. This is how the controller will not see any difference whether it's working with an actual power stage or a virtualized power stage, because all the information that is coming back to the controller is the same one like from real power meters or power analyzers. And this is it. Of course, you don't have to make this kind of settings every time you run the model. You can save the settings and just load them once you want to run this simulation. So you can see that this settings file is automatically mapping all control feedbacks, and also is setting the initial states for our sources that we are using for the grid. Inside the system, there is a built-in scope that we will use to observe the signals. So without further ado, we can now run the simulation. These scope settings are also included in the settings file we loaded a few minutes ago. What we are observing right now, we are observing grid voltages here, grid currents. In this viewport, we are going to observe the currents coming from the controller, from the energy storage or battery storage controller. And here, we are going to observe the currents of the solar inverter. They are both right now disconnected from the grid. What you can see here, these are the currents coming as attempts from this controller to get connected to the grid, and that's it. So now we will undock the scope so we can move to the HIL SCADA, and that we can start running some tests. I will just open one example of the test interface that you can build yourself, again, just by dragging and dropping different elements in the library. I will show you even how you can make some of these elements later during the demo. So let me show you around what we are, let me introduce you what you are seeing In this part, we are observing the measurements from the grid. We can see grid line-to-line voltages, we can see grid currents, and we can also see some power measurements that we right now have in the point of common coupling of our system. We see that we are right now connected to the grid. Here we can also switch to the genset at any point and see how this is going to affect our converters and our controllers. You can see right now when we are connected to the genset, we saw that this switch affected the frequency of the generator, and since there is a governor model inside, we see that that here the frequency is stabilizing, and we can see what is the output power of the generator. We can see that it's quite close to the power that is being consumed by our constant load. We can see that the constant load is right now pulling roughly around 11 kV of power. If we, let's say, decrease the load, we can see that the genset is now pushing, again, the power that is quite close to our load, and we were able to see that this also affected the decrease of the grid currents here. And then let's slowly start the controllers. First, we can start the energy storage controller. You can see here the zero currents appearing as the P and Q references are both set to 0. If we increase the P reference, let's say we can put 100 or 1 kV in this case, we can see the currents here appearing. These are the currents that are coming from this controller F2808. We can see that the battery state of charge is slowly coming down, so we are discharging the battery since we are pushing 1 kV to the grid. When we change this, you can observe, for example, grid currents. Now they are slightly smaller. If I take away this 1 kV coming from this energy storage, you can see that now the currents increased again because we are again feeding this load solely from the genset. Let's now switch back to the grid. You can see that this switch crashed our controller and it's not able to connect back to the grid. So this is again one perfect example of how these kind of tests bring benefits comparing to testing in the actual power line. So now when we turned off the controller, you can see that the grid is again stabilizing. We can switch the controller back on and start injecting different disturbances both from the side of grid and as well from the side of the converter itself. For example, we can very easily unbalance the grid. You can see right now that the grid voltages are different. You can see here on this graph, and you can see how this is affecting the energy storage controller that we are observing right here. Or some different tests, grid harmonics, for example. We are injecting harmonics from the side of the grid, and you can see how this is affecting the currents of our converter. Then we can also simulate, for example, transmission line faults, line-to-ground faults. Take a look. One of the lines is connected to the ground. There is a fault in our transmission lines, and this is how this is affecting energy storage converter. Let's switch back to the nominal regime and cancel this fault back to no faults. What is very hard to perform in the actual power lab is also simulating the converter faults. When you are driving the test on actual converter, it is very hard to simulate, for example, an IGBT fault, like you can see right here. One of the IGBTs is not conducting right now, so you can see how this is affecting the currents of the converter. So these are just some few simple examples of what can be done. Now let's also enable this solar converter that we have. Let's enable him to connect to the grid. There is a 10-second period between different attempts for this converter to get connected to the grid. There we go. Now it's catching up. Now you can see grid currents appearing here, and here in this monitor we are tracking MPPT in real life coming from this converter. So let's take a look. If we are increasing the load power, you can see that now this is lowering the grid currents, as most of this load is being fed by this solar inverter right here. If we increase the load even further, you can see that this continues. And just you can see that now we are running this solar converter is feeding 32 kV of power and feeding 23.5 kV load. So relatively close numbers. Let's see what happens when we inject some harmonics into the grid, and we slowly increase this power toward the numbers that are close to what solar inverter is feeding. Take a look how this affects the behavior of this controller. So as long as the grid was stable and we had the clear sine waveforms in the grid, this converter was performing perfectly well. But as soon as we have the appearance of some harmonics, you can see how this is affecting the behavior of the converter. If we switch back to the nominal regime and we don't change the load power, you can see that now the converter is again working quite well in the stable regime. So these are just a few examples of what can be done in this kind of environment, just to understand how complex it is to make this kind of testing interface. I will just show you a few examples. You can see that all these elements are available in our library on drag and drop options. I will unlock this environment, and let's make this kind of gauge that is going to measure the line-to-line voltage of the grid. You can just drag and drop the gauge to our working area, double click on it, and just say which signal we want to observe. We want to observe RMS signal measurement of the grid, click OK, and then just add maximum amount. We are expecting that to be over 500. On the click OK, take a look. This gauge is already working in real time, programmed only with our mouse clicks. Another part that was also mentioned during the presentation of our guest lecturer Alvaro is how easily you can make this kind of buttons that are going to initiate different testing scenarios. For example, if we want to add harmonics to the grid, we will use a macro button, and then what is behind these buttons is open source Python environment where you can also write your own test scenarios from the scratch. For those of us who are not Python experts, there is a built-in API wizard that allows programming these buttons completely graphically. For example, if we want to add harmonics to the grid, we can do this just by saying, okay, harmonic number 5, let's say 0.2, 0.1 per unit. If you click OK, you can just go to the part of the code where you would like to have this kind of disturbance inserted and click Insert. So this API wizard allows you to write this kind of test scripts automatically. If we come here and press play, you can see that this ejected the harmonics into the grid and crashed both our controllers. So we switch to the nominal and then reboot these controllers. Okay, this one is going to reboot automatically. So this is where I would like to conclude this demo. Before we go to we switch back to the Dragon, I just want to show you a few examples of how this controller here technology is being used by different customers in different applications. Much more detailed explanations are available on our website. Here there is a very nice example from hybrid vehicles applications from Liebherr, Much more detailed testimonials can be found on our website. Another example from active filter applications, this is Schneider Electric company in Oregon in the US. Here you can actually see the first commissioning or the first test run where the controller was actually connected just by simple wiring. Few more examples, solar inverter controllers connected in parallel, 12 inverters connected together, so this is going closer to the field of microgrids. And another example of a double-fed generator inverter, you can see the control system right here connected to the HIL box, and you can see the slight differences in the engineering approaches here. Another very interesting example, 8 megawatt battery storage integration project in South California Edison utility in California. You can see here the testing facility. Another example from the field of drives. This is ABB medium voltage drives division in Turkey. This was the testing facility that they tested their controllers before Typhoon HIL, and then this is how their testing facility looks today. The original control system connected to the virtualized, completely virtualized power stage simulated here in this box. And finally, I would like just to announce that in one of our next webinars, we are going to show a different example of how this technology can be used in testing of microgrids and microgrid controllers. So please stay in the close watch or sign up for our newsletters if you haven't signed up already, so you can get notified when these webinars take place. And the final example that we mentioned in our introductory presentation, this technology, this example that we showed today, is already harnessed in Austrian Institute of Technology for pre-certification of solar inverters, as it is quite clear that the majority of procedures in these fast-evolving and quite advanced grid codes and different connectivity standards are targeting control functions, including the ones like low voltage write-through that was mentioned by our guest Alvaro Luna, and also anti-islanding in the part of the IEC standards, etc. This is an example. This is just parts of the reports that are being generated by the completely automated test suite that is being run by Austrian Institute of Technology in Vienna.